Inductance. First, what do you mean by electromagnetic induction? Electromagnetic induction, which we studied by varying magnetic fields, magnetic fields with respect to time, produces electric fields or EMF, electric currents we say. Okay, this electric current, how it is produced? Is producing, that's fine. How the production takes place? This production by flux linking with the coil, with the coil. So how much flux is linked with the coil? We can expect that much inducing current, right? So if the coil area cross section is more, then more amount of electric current can induce or EMF can induce, we can say, right? So this we will discuss, right? Flux linking, in the sense how this flux is linking. We will discuss according to Faraday's law, the flux linked by the magnet without touching the coil. And in the same way, electromagnet produces the flux, and due to that also we have induced the current in the neighboring coil. So the flux linking with the coil is produces or induces EMF in its own coil also, in its own coil or in the same coil or in its vicinity. Vicinity, why I am telling, the circumstance, if there is any other coil is there, if the coil, if it is influenced by this flux, then we can say that its vicinity also. Okay, now an electric current can be induced by what? By changing the flux. Which flux? The change, the amount of flux, how much it is there, that much amount of current can produce. That I can write flux, magnetic flux is directly proportional to I. Therefore, since, as I said, by varying magnetic field with respect to time, nothing but change in the flux with respect to time, I can write as both sides are prime and differentiating. Differentiating with what? Differentiating with the time, right? So d5 by dt is directly proportional to di by dt. Of course, if I remove the proportionality, let us say from this equation, coil means always it is having the number of turns like this. Okay, so in number of turns it is applicable. So number of turns increases, what happens? The amount of current also will be increases. So we can say that is proportionality for that, right? So n by d, number of turns linked with the magnetic flux is directly proportional to the amount of current induced in its. Okay, this gives us proportionality constant. From this, if you are taking that, we can write inductance or K, we will take up, or if it is self inductance, it can be taken as, if it is mutual inductance, it is taken as N, right? But this constant proportionality, whatever you are taking, that is, if I'll write as K into I, then this proportionality constant is called as inductance. Inductance. What is that? This proportionality constant is called as inductance. Remember, This proportionality constant or this inductance always depends on the number of turns of the coil, and it is also depends on the amount of flux which is linked with the coil, then geometry of the coil also. What do you mean by geometry? Geometry in the sense how much area does it have? Okay, it depends on the area and shape. If it is proper cylindrical shape and more the area of cross section, then we can say that it is having produces more inductance, or it also produces more amount of current or induces more amount of current. So, since I have considered here n pi b equal to I, therefore I can write n pi b equal to proportional to constant k into I. So k I have taken as inductance. This inductance is depends on geometry of the coil, geometry of the coil, and next this inductance also depending on the intrinsic material. Intrinsic material in the sense, if I use copper wire, the effect is different. Instead of copper, if I use some aluminum wire, the effect is different. So material to material, the effect of or the capacitance of inductance is different. So that's why it is different from the different materials. And at the same time, it is also depends on the intervening medium. Depends on intervening means wherever you are doing this experiment in the time, the medium surroundings, and that it is different. It is depends. That's why it is also called as, we can call as intrinsic property of the material. It is depends. Okay. Now, apart from this, how can I write this inductance? Here, inductance, whatever I am talking, this inductance also having the dimension formula and units. Units for the inductance is, I said earlier, Faraday and Henry both are the scientists has done independently this experiment and given the results. So units has given the name of Henry. Okay. So dimension formula also is there for this. You can write up n L square T minus 2 ampere minus 2. Ampere minus 2, why? Because K equal to n pi b by I is. So from there. Next, if this is all about the inductance and inductance dependent factors, dimension formula and units. Right? Next, we have two types of inductions. What are those? I said already. Self and mutual. Self and mutual. Coming to the mutual induction, first of all. Inductions are two types. One is mutual inductions, and another one is self-induction. So the name itself is indicating mutual and self. Mutual, okay, fine, sir, but how self is possible? That we are going to discuss. Let us see mutual induction first. mutual induction. See, induction in the sense inducing the current by a coil in itself or in the neighboring coil. This we studied in the induction. But mutual induction in the sense, if there is a any coil, okay, let us say this is a one coil which is attached with the battery and connected with the switch. Therefore, obviously, it is if it is acting as electromagnet in the sense, it produces the flux. What it produces? Flux. The way whatever the flux it is producing, this flux, if it is continuously produced like this, obviously this flux affects the in its vicinity. Vicinity in the sense around it, if any wire is available or any coil is available, obviously it gets affected by this flux. Let us see. Here I am using another coil in its vicinity. This is just coil. I have connected with the galvanometer. So obviously the flux whenever it is touching to this, then flux is entering through that. Since the flux is entering, whatever the flux is coming from the coil, it is passing like this. It is cutting this flux. Now here we are having the two coils. This is one way. This we say it is as a first coil. Coil one as a primary coil. This is we can take as a secondary coil. So automatically, when the current flows through this coil continuously, the flux produces. The produced flux, obviously, if it is gets cut by this external coil or secondary coil, in this coil also current will produce. Will produce current produces or current induces. We say current or EMF induces. So this phenomena we call as mutual induction. Now, here you have seen one area. Another area, as per your textbook, as NCRT, they have provided, they have taken the two coils. One is a less area of cross section, okay, and having the radius is less. Now, that it is they have named as S1. In the same way, one more coil they have taken that is S2. S2 in the sense which is having here area of cross section is more. But here, whatever you are finding, these two coils if you are taking from the outside to inside, the radial distance is more for the outer coil and less for the inner coil. This is S2. These coils are called as, they also is in a concept of or in the phenomenon of mutual induction, but these also we can call it as coaxial coils since they are along the same axis. Coaxial coils. Of course, this is also along the same axis but not over each other. Comparing with this, in this case, the effect of inducing concept is more. Why the effect of inducing is more in the sense, since the magnetic field will not go outside. Here there is a chance it will go waste, but here it will not go waste. Every, for example, let us say S2 is the coil acting as a primary. I have connected to the battery, let us say, and S1 is the inducing coil are connected with the galvanometer G to the S1. Then automatically the total flux which it generates or which is produces which acts inward on the S1. So automatically S1 is get influenced by this coil S2. Then in the S1 automatically there is a large amount of EMF as well as such that we say inducing current develops. Right? So this is a phenomena of mutual induction process. But with respect to the coaxial coil, what they have considered, what they have taken, and how we have to bring out in the form of equation or expression is important now. Let us say here S1 and S2, and they're also having all n number of turns in both cases, right? And the coil length also we can take L from both are having the same L, but area of cross sections only is different. Area of cross section for the inner coil they have taken R1, for S1 it is R1, and for S2 it is R2 from the axis to outside. Now, okay, coming to this. Inner coil S1 R1 and number of turns per unit length is small n1. Okay, for inner coil S1 R1 and number of turns per unit length is n1. Let's say. Same way for for outer coil S2 R2 N2 number of turns per unit length we have taken. Now, of course, if you are taking number of tons per unit length, it's N1. Number of tons only if you are considering, let you can write N1, N2 are the total number of tons. Total number of tons in S1 and S2 respectively. In S1 and S2. Next, here, excuse me. Next, here, in this case, if you see, when a current I2 is set up through S1 means when you connect a current to S2, then current I2 passing through S2 set up nothing but passing through S2 in the sense what happens nothing but we have connected a battery to the S2, then obviously when you connect a current magnetic flux produces magnetic flux produces this flux, whatever it is produces, that is through the S1 also will pass since it is inside. To S1. Now, what happened? This flux, let us flux call as phi 1. Whatever the flux is attached linking with the S1, we are calling as a phi 1. Now, the corresponding flux linkage, we can say, the corresponding flux linkage. Why this linkage is, I am telling linkage always is important. Linkage through coil or we can say solenoid also since it is in a solenoid shape. Through coil you can write N into number of turns and flux to the coil 1 that is equal to since coil 1 I said number of turns. Then therefore we studied in the induction definition that is phi is directly proportional to I, right? So the current I1 produces, right? Since the current produces I1 in the coil 1, and at the same time there must be a constant. The constant here we are taking mutual inductance M12. What is this M12? Can anyone? M12 is called as coefficient of mutual induction in solenoid S1 of solenoid S1. Coefficient of mutual inductance of coil S1. Now, this is the equation we got by that for the first case. Now, whatever I am taking flux N1 into pi 1. Pi 1 is in the sense in the first coil. Now, what I am trying to say that here, since it is produced in the pi 1, there are coaxial coils. Since there are coaxial coils, what happens, the same amount of flux induces in that the coil 1, whatever it is produced by the S2. So I can write the number of turns per unit length is N1 into L. N1 into L. Since we have studied in solenoid also, N1 by L equal to N1, right? So I can write like this. Now flux formula B into A. Flux equal to magnetic field into area of cross section that we know, right? Since it is passing through the solenoid area of cross section is pi r square. Since we are talking about 1 pi r1 square. Now magnetic field through the solenoid is how much? Did you remember the expression? Magnetic field through the solenoid B equal to mu naught Ni, right? So this mu naught Ni in the coil 1 we can write as here mu naught N2 I2. Why I have used N2 I2? Because the current which has produced in the coil 1 due to the coil 2 only, no? So mu naught N2 I2 ampere. So next, here this is further I can write as the total expression mu naught here N1 N2 N1 N2 and L into pi R1 square into I2. This is N1 pi 1 equal to. Now the same thing will happen whenever you have written reverse effect. Reverse effect in the sense, if you are set up current in the I1 in a S1, then by that if you are trying to induce in the coil 2, also same effect, but numbers will be changes in opposite direction. But since same material and same flux is linkaging with the both, so the effect I can write here since this formula. In this place only we have written now this all because N1 pi 1 equal to this we have written. So what I am doing here, simple is a small change in this equation, M12 equal to. Are you there? Are you following?
Yes, sir.
But I did not find any question in the middle. M12. M12, what I said, coefficient of mutual induction of S1 with respect to S2. That equal to I can write up when I am comparing this equation with this equation. Okay, I am comparing. So M12 equal to I can write as this mu naught N1 N2 into L into pi R1 square pi R1 square into L. So there also current, here also current. So current dimensionally I am not taking. So coefficient of mutual induction of coil 1 with respect to 2, I have the value is this. Now this is when I set up a current in I2, I produce the current in a coil 1. The same thing if I'll do, if I'll set up the current in I1 or coil 1, if I'll produce the current in S2 means coil 2, then therefore I'll get the effect of mutual inductance, coefficient of mutual induction of coil 2 with respect to coil 1 that I can write as nothing but N2 pi 2 equal to M21 into I2. This is the same thing we have written in coil 1 case. Okay, there it is. I1 we have written in the first case. Okay, I did a mistake here. So due to the this is I2. Here it is I1. Here it is I1. So due to this, whatever it has produced, same thing. N2 pi 2 equals also I'll get the same expression mu naught N1 N2 pi R2 square of length is same in both cases, right? So here it is I1 means here also I'll get I1. Therefore, finally, what I'll get here M12 equal to I'll write as a sorry 21 equal to same value mu naught N1 N2 pi R2 square L only I'll get. Why? Because the mutual inductance of the coil 1 and coil 2 are same because their area as well as number of turns and the unit length also same. The in the same medium we are doing the permeability also same. So that's why we can write from these two expressions equation 1 equal to equation 2. This is the 2 1. So I can write M12 equal to M21. So which is also called as M we can say. So mutual inductance between the coils, coaxial coils, whatever we are trying to induce current one to another or second to first, whatever. But mutual inductance remains same in both cases. Mutual inductance is belonging to the process of two coils. So the coefficient remains same in both cases if dimensions and all is same in both cases, right? So this is all about the mutual inductance concept uh, in the coaxial process. Here, before that, there is a one small change. Since here I2 I have taken, then here also I2 I'll get. Yeah, it's correct now. Everything is fine. Anything doubt in this expression or in this derivation? Uh, Simon,
No, sir.
we following now. Here two coils were there. In one coil we set up a current. We have produced the inducing effect in the another coil. That is in the first case. Okay, we
Yes, sir.
achieved this is the equation first one. How did we achieve? We know that here n number of turns that is per unit length we have written this and pi equal to magnetic field into area flux equal to okay magnetic field through the solenoid expression is B equal to mu naught Ni. This is also we discussed in previous lessons. So again the area obviously area of the cross section of the coil pi r square only. So in which coil we are doing in the first coil? So R1 square. But in the second case it is with respect to the second coil, so R2. So already we have obtained from the inductance this formula. So it's these two, this N2 phi 2 equal to if it is this in the sense, this is also equal to this one, right? So I1 cancel from the both side. You are having N2 one equal to this value. The same value you will have here with respect to the N1. Okay, M1. So
Yes,
now here both are whenever are equate, then both cases the mutual inductance remains same. Since the mutual inductance is same, then what happened here? We can say if you are inducing the field or EMF or a current in the neighboring coil, which is same material if you are using, then the mutual inductance and the flux linkage with that is same. Remember here, the area of cross section here it is also R1 square. In the previous square also same as R1. Yeah. So this is what mutual inductance concept. Now we have studied in the previous topic affecting factors of the inductance. Here coefficient there we have studied inductance as a K. Here Mutual inductance or coefficient of mutual inductance is M variable. Okay, this is depends on what factors it is depends. The flux linking with that always, and number of turns n which is in the coil, this we know, and geometry of the coil. And apart from this, the medium which we are using in, nothing but we say it is intervening medium is most important. And unit same as for the mutual inductance also Henry. Okay, so this is all about the mutual inductance. Next, we will discuss some numericals. Then we will get a little more clarity on the concept. Okay, so